In order to solve equations, we have to understand how opposite operations work. One way to see opposite operations would be to look at these two equations. 3 plus 8 equals 11, and 11 minus 8 equals 3. This is why addition and subtraction are opposite operations. And I want you to focus on an equation saying, if you start with the number 3, add 8, it will equal 11. So that if you start with 11 and subtract 8, you'll end back up at 3. The other pair of opposite operations, multiplication and division. 5 times 7 equals 35, so 35 divided by 7 equals 5. And again, we can see how starting with a number, 5, and doing the operation of multiplication by 7 equals 35, so taking that answer 35 and undoing the multiply by 7 with divide by 7 will get you back to that starting number 5. And using this idea about opposite operations, we're able to solve all four of these equations. In the top left, x plus 2 equals 9. So starting with some number, if we add 2, it equals 9. So we'll do the opposite. We know that x equals 7. So spotting the variable x and seeing after it add 2, I'll do the opposite, take away 2. And when we do 9 take away 2 equals 7. Looking at the subtraction problem, x minus 14 equals 2, so we'll do the opposite. From the number x, instead of take away 14, we will add 14. So 2, when we add 14, we see x equals 16. Here's a multiplication. The variable x is being multiplied by 6.3. So we'll do the opposite, divide by 6.3. When we do 27.72 divided by 6.3, x equals 4.4. And the last one, x is being divided by 3 to equal 2.8, so we'll do the opposite, multiply by 3. And so x equals 84. So now let's take these ideas into a more complicated problem. But the more complicated problems really use the exact same concept about opposite operations. They just have more operations going on in the equation. For a quick example, let's take this number 5.16. And to this number we'll do a few operations. First, let's take away 3. And now we're down to 2.16. Then we're going to multiply by 7, equals 15.12. And now we'll add 8 to get 23.12. So from some starting number, we have a series of operations that leads us to a final result. Understanding how opposite operations work, if we take 23.12 and we undo each of these operations, we'll end back up at 5.16. And the key is that we have to undo them opposite order from when they happened. So the last thing we'll do is that take away 3. We have to undo each of these steps that occurred. So opposite of add 8 would be subtract 8. And that takes us to the 15.12. Next we are undoing the times 7 with divide by 7. And we get 2.16. And last undo minus 3 with add 3. And we get back to 5.16. And how this relates to equations would be our original number, we don't know exactly what it is to start with. But if we know all the other operations and what our final answer equals, we can undo all of those operations to find the original number. If we were to write this as an equation, with our original number unknown, we'll use x. First operation, take away 3. Once you take away 3, we will multiply by 7. We had to use parentheses because that's how we represent subtract first and then multiply by 7. After that, add 8, and it equals 23.12. So here's the equation that represents a set of operations. Starting with an unknown number, x, we take away 3, then multiply by 7, and then add 8. Just doing our order of operations with this expression on the left side of the equation. And we know that it will equal 23.12. So now we can take a look at a way of writing all of these opposite operations in the opposite order that they happened. How we solve this equation, find out what does x equal. That is the number that will make this equation true. It will make all of this on the left side equal 23.12. So I've rewritten that equation up here, and again, we see what operations happening to the variable x. We see first we would subtract 3, then multiply by 7, and then add 8. So we need to undo each of these steps starting with the add 8. We'll undo it with take away 8. So let's go ahead and take away 8 from our result here. It's helpful to mention right now that we do look at equations as being balanced when they're true. That everything that we see on one side of the equation, thinking that the equal sign cuts it in half, everything that we see on one side equals everything that's on the other side to keep this equation balanced. So when we subtract 8 from the left side, we're subtracting 8 from the right side also. We need to do these moves to both sides of the equation to keep it balanced. But remember, we're just undoing an add 8 with a take away 8. We're just showing that those operations, you could say, cancel each other out. Because we know add 8, then subtract 8, you're exactly where you started. Those are opposites. So this subtraction is what gave us the 15.12. And now, after undoing that addition, we have only left take away 3 and then multiply by 7. So let's undo multiply by 7 next. Undo this multiply by 7, divide by 7. So going to our current result, 15.12, when we divide by 7, is when we get to 2.16. The multiply by 7 and divide by 7 are opposites, so now we're left only with the subtraction. X minus 3 equals 2.16. So hopefully you can see it already, but we'll just wrap it up. Undo subtract 3 with add 3. So to our final answer, when we add 3, we get 5.16. So that would be the flow if we started with an unknown number, how we could figure out what that number is. And we undo each step, each operation occurring to the variable. And the steps that we've gone through here are the exact same steps that we did here. This is just a much more algebraic representation when we start with an unknown number. But notice that we were doing the exact same steps from 23.12, subtract 8 to get to 15.12, divide by 7 to get to 2.16, and add 3 to get to 5.16. That was our unknown number in this equation. Here's our next example. Starting with the variable, we're multiplying by 2, then subtracting 7, then multiplying by 3, then adding 6, and it equals 42. So now we're looking at 4 operations that we might have to undo each one, but there is a simpler way. That's why it's called simplifying. That means we're looking for where can we distribute, and then do we have any like terms we can combine. So spotting a set of parentheses, definitely we can simplify. We multiplied this number to each term inside the parentheses. That should give us 6x minus 21. We were able to simplify just this term. We still need to show the plus 6 equals 42. As we're doing simplifying on an equation, we're only focusing on one side at a time. So we're just bringing down equals 42. I'm only focusing on distributing and combining like terms. So next, I want to spot negative 21 plus 6. Those two equal negative 15, and we still have this 6x. Now we have to stop simplifying the left side at this point because we don't have like terms. We can't subtract when one term has a variable and the other is a constant. It doesn't have a variable, it's just a number. Addition and subtraction are just not possible with terms that are not like. But we did accomplish simplifying this equation. It's easy for us to see the two operations occurring. Multiply by 6 and then subtract 15. So we'll first undo the subtract 15 with add 15. That's going to bring our 42 up to a 57. And now the last operation, multiply by 6, undo it with divide by 6. I usually prefer to keep an answer that is a simplified fraction, if it's in fraction form. 57 doesn't divide evenly by 6, but these numbers are both divisible by 3. So we could simplify this to 19 over 2. It's fine as a decimal also, 9.5. So our approach with equations is look at each side of the equation one at a time. And what can we do to simplify that side of the equation? We're thinking distribute and combine like terms. Eventually there will be nothing left to simplify, and then we do the opposite operations and get to the answer. Now here's an example for you to try, so pause the video, try this one, and then restart the video and we'll look at the answer together. First we are distributing. Multiply the 2.7 to each of these two terms in parentheses. That left us with 4.05x minus 8.1 equals 4.86, the other side of the equation. Now do we have any like terms that we can combine And we do not. We have one variable term, one constant term, so nothing else to simplify. We're now looking at undoing these operations. The variable is being multiplied by 4.05, and then we take away 8.1. So let's undo take away 8.1 with an add 8.1. So it gives us 12.96, and that's the result of just multiplying 4.05 times the variable. So let's undo that last operation, the multiply by 4.05, with divide by 4.05. And when we take our answer, divide by 4.05, we get 3.2. So x equals 3.2. And we can check this solution if we take 3.2 and put it in place of this x right here in the equation. It will make the equation true. When we evaluate the left side, we'll see that it does equal 4.86. Next is kind of a nasty looking example, but we've got an approach that will simplify first. So take these sides one at a time. Look just on the left side first. We can distribute 3 times 1.5m, 4.5m, and 3 times minus 2 minus 6. We still have this positive 2.1m. Now do we have like terms? 2.1m plus 4.5m, these are both variable terms, so we can add those two. 6.6m minus 6, the constant term, and that's as far as we can go with simplifying the left side. On the right side, we can distribute 1.5 times 4m is 6m, and 1.5 times minus 1 minus 1.5, and plus 1.8. Now the like terms on this side are the constant terms. We have two constant terms we can combine for a positive 0.3. So we have 6m plus 0.3 on the right side of the equation. Now we've done all the simplifying that we can, but we have our variable in two different places. They're on opposite sides of the equation. We definitely cannot try to just combine those two, because simplifying we only do to one side at a time of the equation. We can't mix these two that are on opposite sides. But we can still use our ideas of opposite operations, and that we keep these equations balanced. So there are 6.6m on the left side and 6m on the right side. If we do the opposite of this positive 6m, take it away, and say keeping the equation balanced will take away 6m from the left side, this is how we have to put together terms that are on opposite sides of the equation. We really have to think about removing it from one side and removing it from the other side to keep things balanced. And so 6m minus 6m, opposites are gone. We're left with, on the right side, just this 0.3, and I skipped over, but I didn't forget this minus 6. So we subtracted this variable term so that we have a variable term only on one side of the equation. And this positive 0.3, we actually don't have to write the plus, it's just a positive 0.3. So now let's undo this take away 6 with add 6. That'll bring us up to a 6.3 equals 0.6m. And last, we'll undo multiply by 0.6. I'll squeeze it down here with divide by 0.6. And 6.3 divided by 0.6 gives us our value for m. m equals 10.5. So I'll put up one that's similar for you to try. So pause the video and try this one. And now restart, we'll look at the answer together. The left side we can distribute first. 3.2 times 2x equals 6.4x. 3.2 times negative 5, negative 16. We have another variable term, a positive 5.6x, that we can combine with the 6.4x. It equals 12x, and we still have the constant term, minus 16. So a variable term, a constant term, nothing else to simplify. Let's move over to the right side. Distribute 2 times 1.4x equals 2.8x. And 2 times negative 0.6 equals negative 1.2. And the constant term positive 3.6. Now we have two like constant terms, 3.6 and negative 1.2, or 3.6 minus 1.2, same difference equals 2.4, plus the variable term 2.8x. So the variable shows up on both sides of the equation again. Let's take away 2.8x. Make sure we hit both sides. So we have left just 2.4 on the right side. With 12x, subtracting 2.8x leaves us with 9.2x and the constant minus 16. And now we're ready to finish solving this equation. Undo the minus 16 with plus 16. That takes us up to 18.4 equals 9.2x. And last, undo multiply by 9.2 with divide by 9.2. And that leaves us with x equals 2. Lastly, let's talk about equations that use fractions. First, we want to be able to recognize a proportion when we see it. An equation where each side is only a fraction. There are no other terms. There are lots of different ways for solving proportions. One common way is that we cross-multiply. A lot of people will call it that we multiply the numbers diagonally and then divide by the third number. That approach always works, and it's a very quick one to go to. 2 times 15 equals 30, and then divide by 3 equals 10, and that's our result, that fourth number. It must equal 10. But I want to talk about some other ways to solve proportions where we really clearly see why we're doing these moves. First of all, we know about fractions that they are equivalent when we multiply or divide the same number to numerator and denominator, both parts of the fraction. So if I can see that 3 times 5 would equal 15, and I know multiplying by 5 in the numerator would give an equivalent fraction, there's another way that we can spot that x equals 10. But not every proportion will have numbers where it's so clear to see what we need to multiply to make one fraction equivalent to another fraction. Like in this example, 2.15 over 7.74 equals what number over 27? It's not clear what do we multiply to get from 7.74 over to 27. If we can spot how we get from one denominator to the other, we'll know exactly what we need to do to the numerators. But remember what we know about opposite operations. We don't know what we're multiplying by to go from 7.74 to 27, so we'll do the opposite. 27 divided by 7.74. Now this number turns out to be kind of a nasty looking decimal, but don't round or anything, but we do know that that's the number, hopefully it's in your calculator from that division, that we need to multiply to 2.15. And when we do that, we have a much more pleasant result. X equals 7.5. We're doing the same basic steps in this example. We divided and multiplied, and it's helpful to remember that in this fraction the numerator works like a multiply, the denominator works like a divide. So from 27 we divide by the denominator and multiply by the numerator, and that equals x. But there is one last way that we should cover, which is the closest to what we've been doing using opposite operations. There's our variable, and it's undergoing an operation of divide by 27. So we can figure out x if we do the opposite, multiply by 27. Divide by 27 and multiply by 27, they undo each other, they cancel each other out. Just remember that we multiply this side by 27 also. And multiplying 27 by this ratio equals the same 7.5. So there are several ways that we can solve proportions. It's helpful to know about the variety of ways that we have, and we'll use some of these ideas in the next couple of examples that we look at. So let's talk about how we can approach solving this equation. We can definitely think about the operations on the variable and undoing them. So we could say, if you start with t, first you add 3.5 and then divide by 6. So if we do the opposite of those, go over to the 8 and undo divide by 6 with multiply by 6, that will give us 48, and we undid the divide by 6, so now we have left just t plus 3.5. And now undo adding 3.5 by take away 3.5, and that will give us 44.5 for the value of t. Another approach would be to work this like a proportion. We have only one term on each side, clearly a fraction on the right side, and remember the whole number 8, any whole number we could write as a fraction, we put it over 1. And now we are looking at a proportion. At this point we could still say I'm going to multiply both sides by 6. It's going to look a lot like how it went down over here. Or we could say, to show that these two fractions are equivalent, in the denominators 1 times 6 equals that denominator 6, therefore 8 times 6 has to equal this t plus 3.5. 48 equals t plus 3.5. Now they're all valid moves, so of course at some point they're going to all look exactly the same as we work our way down to t equals 44.5. And I think it's best if we don't try to focus on one set of steps to memorize, but have a better understanding of fractions and opposite operations to see a few different paths through these problems. So here's a quick example for you to try. X over 2 plus 3 equals 15. Choose any approach to solve this equation, and now restart the video. We'll look through some answers. The equation right now is not a proportion. We see a fraction here, and we can think of that 15 as a 15 over 1, but we have an additional term over here. So we're not ready to start handling it like it's a proportion yet. But you could look at the variable x and identify the operations, that it's dividing by 2 and then plus 3. So divide by 2, then plus 3. We'll undo them with a take away 3, so that equals 12. And if x divided by 2 equals 12, let's do the opposite of divide by 2, multiply by 2. And remember, we do always find the variable to see what operation is going on to the variable to help us choose what the opposite operation would be. So the multiply by 2 and the divide by 2 are done. It leaves us with x equals 24. So here's our last example. 37 equals 12 plus 5 over n. We're trying to figure out what does n equal. We can see that this fraction would then be added to 12. So let's go ahead and take away 12, undo that operation, and 25 equals 5 over n. Let's think about what options we have for solving this equation. We can write the 25 as 25 over 1 and work the proportion. If we think cross multiply, 1 times 5 is 5, and then divide by 25, that will give us n equals 0.2, or 1/5. If you looked a little bit more closely at these two fractions and said, if we do 25 divided by 5 equals 5, therefore 1 divided by 5 equals n. And 1 divided by 5 is 1/5, or 0.2. So still a proportion, but a slightly different way of looking at it. Another approach would be to do something similar to what we did with the last problem. The way we dealt with a fraction would be to understand that the denominator works like it's dividing, so do the opposite of divide by n and multiply by n. Dividing by n and multiplying by n, those are still opposites, even if we don't know exactly what n equals. And n times 25 on the left side would give us 25n equals 5. Now this looks a bit more familiar, and we can divide both sides to undo multiplying n by 25. Divide by 25, and again we'll see that n equals 1/5, or 0.2. Now don't get bogged down in this variety of options that we have. Think about our main steps, that we try to do some simplifying at the beginning of an equation, one side at a time. Then we begin to undo some moves that are like canceling out terms so that we can get closer and closer to where we see the variable. It's helpful because problems do come in a variety of ways, so we need to have a variety of ways to solve them, whether it be finishing with a proportion or seeing a set of opposite operations that we can perform.